Hello friends, I welcome you in lecture number 10 on Laplace transform. In previous lecture we have discussed first shifting theorem, and we know that we will apply first shifting theorem if we have multiplication by exponential function. If our function f of t is multiplied by exponential function, then we can apply first shifting theorem. And first shifting theorem says that if Laplace transform of function f of t is capital F of s, then Laplace transform of that function multiplied with exponential function is given by replacing s by s minus a in f of s. Now suppose we have multiplication of given function f of t by some positive power of t. Suppose we want to find out Laplace transform of function f of t which is multiplied by t to the power n, where n is a natural number. Then this Laplace transform is given by this formula minus 1 raised to n times derivative with respect to s of the function f of s, where f of s is Laplace transform of function f of t. So whatever power is given, we have to differentiate this function of s that number of times. Suppose power is 1, then our formula will be Laplace transform of t times f of t will be equal to minus 1 raised to 1 derivative of f of s with respect to s, first derivative. If we take n equal to 1, here we will have n equal to 1, that is one time derivative of this function f of s with respect to s, and minus 1 raised to 1, that is minus 1. So we will use this formula if we have power of t in the product, and if we are familiar with the Laplace transform of this function f of t. So we will remember this formula as multiplication by t raised to n. If Laplace transform of f of t is capital F of s, then Laplace transform of f of t multiplied by t raised to n is given by minus 1 raised to n times derivative of f of s with respect to s, where n is natural number. And for n equal to 1, we will have Laplace transform of t times f of t equal to negative of derivative of f of s with respect to s. We understand this formula with this example. Find Laplace transform of t times sin 2t. So if we compare with t raised to n times f of t, then here n is 1 and function f of t is sin 2t. So first we find out Laplace transform of sin 2t, and we have ready-made formula for the Laplace transform of sin function. It is given by 2 divided by s square plus 2 square, that is 2 divided by s square plus 4. This is our function capital F of s. Now here power of t is 1, so therefore Laplace transform of t times sin 2t is equal to minus derivative of this function f of s with respect to s. So this is equal to minus d by ds of 2 divided by s square plus 4, and we can easily find out derivative of this function, minus 2 as it is d by ds of 1 divided by s square plus 4, and the derivative of this is equal to minus 2 into minus 1 divided by square of s square plus 4 into derivative of s square plus 4, which is 2s. So here we are applying chain rule. We know that formula for derivative of 1 by x is minus 1 by x square. Instead of x we have s square plus 4. So we write minus 1 divided by s square plus 4 square. And by chain rule we have to multiply by derivative of s square plus 4, which is 2s. And if we rewrite this, we can multiply minus 2 and minus 1, that is 2, and 2 into 2 is 4, so it is 4s divided by s square plus 4 whole square. So in this way we can find out Laplace transform of f of t multiplied by some power of t. So we can construct another function and we can find out its Laplace transform using this formula. Suppose instead of single power, suppose I am having t square, and instead of sine function, suppose I have cos 3t. Then first I have to find out Laplace transform of cos 3t. We have ready-made formula for the Laplace transform of cos function, which is s divided by s square plus a square, a equal to 3 here. Therefore Laplace transform of cosine function is equal to s divided by s square plus 9, and this we denote by capital F of s. Now here cos 3t is multiplied by t square. So now we find out Laplace transform of t square cos 3t. So because we have n equal to 2, we write minus 1 square and 2 times derivative or second derivative of f of s with respect to s. Square of minus 1 is 1. This we can rewrite as d by ds of df by ds. So first we take derivative of f of s, and whatever we obtain that we will differentiate again, and f of s is s divided by s square plus 9. So I write one more step. I first substitute value of f of s, which is s divided by s square plus 9, and whatever we will obtain here, that we have to differentiate again with respect to s. First we write down derivative of this. Here we apply division rule for derivative. In the denominator I take square of s square plus 9, and I keep s square plus 9 as it is. Derivative of s is 1, minus s as it is. Derivative of s square plus 9 is 2s. So first we simplify this derivative which we have obtained. We keep this as it is, s square plus 9 whole square, and this we write as s square plus 9 minus 2s square, and again we rewrite this function. Here we have 9 s square minus s square is minus s square, and here square of s square plus 9, and we have to differentiate this again with respect to s. So this is now problem of differentiation. We again consider square of s square plus 9 square, that is 4, s square plus 9 square as it is. Derivative of 9 minus s square is 0 minus 2s, minus 9 minus s square as it is. Derivative of s square plus 9 whole square is 2 times s square plus 9 into derivative of s square plus 9, which is 2s. Now here if you observe, we have s square plus 9 whole square and here s square plus 9. So we can cancel out 1 s square plus 9 with this denominator. So we directly cancel out s square plus 9. Here we will be having 3 power, and here I write in this way minus 2s. S square plus 9 is cancelled out, and here minus this 2 into 2s, that is 4s times 9 minus s square, and this s square plus 9 is cancelled out. Here 1 s square plus 9 remains, that we have written here, into minus 2s. This 9 minus s square as it is, 2 into 2s is 4s, and s square plus 9 is cancelled out. And now we modify all these things. We can take minus 2s common, and we are left with s square plus 9 here, and here if we take minus 2s common, there will be 2 in the product, and that we can multiply with this bracket, and minus sign is taken outside, so we have 2 into 9, that is 18 minus 2s square, and this remains as it is, s square plus 9 raised to 3. So now we again rewrite s 18 plus 9, that is 27, s square minus s 2s square, that is minus s square, divided by cube of s square plus 9, and this we can again rewrite by taking negative sign inside, and we have s square minus 27 divided by cube of s square plus 9. So therefore Laplace transform of t square times cos 3t is obtained using that formula. We have obtained Laplace transform of cos 3t, and then that Laplace transform is differentiated 2 times with respect to s, and this is simplified form of that derivative. So in this way we can obtain the Laplace transform of function f of t, which is multiplied by t raised to n using this formula. So remember this formula, this is equal to minus 1 raised to n times d raised to n by ds raised to n of Laplace transform of f, that we denote by capital F of s. So this is another formula for Laplace transform. So far we have obtained different formulas for Laplace transform, and we have discussed linearity property also, and now we are discussing this type of things, that how to find out Laplace transform if it is multiplied by exponential function, how to find out Laplace transform of function f of t which is multiplied by t raised to n, that is power of t, which is positive integer, and we will remember these two formulas. This we will remember as first shifting theorem or multiplication by exponential function, and this is multiplication by power of t. And if we remember all these formulas, then it is very easy to decide the Laplace transform. So we have to think that given function is in which form, whether we have exponential function in the product or whether we have t raised to n in the product, and we have to take the decision accordingly. So this is all about this session. I hope you like it. Thank you very much.